All right. Let's take one more motion example. Let's go to a roller coaster. And today's roller coasters are kind of crazy. Let's take that. I'm not going to imaginatively draw a corkscrew or something like those. But let's say down here is a large spring. Now we do it with electromagnets, not springs. But it can be done. And let's say this is compressed 10 meters. That's pretty far. Across the width of a room, probably. Let's say the coefficient, or the K for that spring constant is pretty stiff. And let's say that's 10,000, the weight of a car basically, newtons per meter. So going in 10 is like having the weight of 10 cars getting compressed into that spring. My question is, how far up that hill are we going to get if we just let that car get flung out? So here's where we start with our car. Okay, there's where we end with the car up that hill, and we're going to assume that the track doesn't take away energy. It's frictionless. So what kind of energy is this? This is potential energy. Potential to do work, but it's a spring energy. Okay? Spring energy is governed by 1/2 kx squared. K is this constant, how much it takes to push that spring every meter. X is the distance it gets pushed. And we're going to put the energy up here in what? Potential energy, or energy of height. That is just equal to mg y. Okay? Now, it's not just me and this little guy here, so I can't just say it's 100 kilograms, but let's say me and the car are 200 kilograms. Okay, it's bigger. In Texas, we've got to make it bigger. That we're going to make it 400 kilograms. Oh, what the heck. Let me get in there and make it 500 because I know the math's going to end up a little easier. 500 kilograms. Okay, maybe there's 3 or 4 cars and several people. So we got a 500 kilogram car down here. It's compressing the spring by 10 meters. So if I want to figure out how much energy is stored in there, I'm going to plug these numbers in, and I'm going to set it equal to this one over here, and this potential energy. So let's plug those numbers in. We've got 1/2, the spring constant, 10,000. Okay, that's newtons per meter. Every meter that you extend that in, it's going to give 10,000 newtons out, times the distance squared, which is 10 meters compression. So let's kill that guy. Okay, that's the energy that has. 10,000 times 10 squared and half of that. Potential energy up here is what we're looking for. We still have the mass, which is 500. Me and 5 of my good friends. It's gravity. Let's just keep it simple. 10 meters per second squared times the height, which is what we're looking for. That's the only thing we have to find in this is the y. Now, when I multiply these guys out, this is going to become 5,000. Multiply this out, that's 100 times 10,000. That's going to be 10. It's going to be 1 million. Half of 10 million is 500,000. Okay. So the height is going to be 5,000 into that, which drops these zeros out and takes that into a 1. So the height gets to be, actually pretty awesome. Let's go over here. So the y, if I solve for that, ends up becoming 100 meters. Now, I'd hate to even see what that spring is like, because that spring would be nasty strong. Probably be like a shock on the bottom of one of those huge earth movers or something. But the magnetic ones that they use, the induction coils, and they use electromagnetics, is literally can get that kind of movement out of there. Now, 100 meters in the air is ridiculous. I think even the one in Texas is only 70 meters. I'd have to look Texas Giant for a roller coaster. So That may be a little overboard, but it gives you the idea of what's left. I had kilograms here, meters per second squared, kilogram meters per second. This had a meter squared, but a meter on the bottom, that leaves me 1 meter. That's matching this. The Newton is kilograms times meters per second squared. That gets rid of, meters over meters, so that leaves me just a meter. And we can work those out. That's always important just to double check. You may think I kind of blew that through, but that's okay. That we knew we were coming up to a y. If I run my numbers and I understand what the metric system's representations of those metrics are, they can confirm that work. If you're not, you just get the number 100 and you're like, yes, I'm done. So with that in mind, we can set different energies equal to each other, and that way you would have the chance to do the problem and solve that much easier than we would have if we had to figure out what's the acceleration over here and how far it would go, and then we'd figure out the deceleration. Energy equations are always making problems easier.